Hello, this lecture will cover pages 123 through page 126 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on combinational logic circuits, part F, the diode and transistor. Starting out on page 123, I'm going to define two semiconductor devices. First of all, the diode. The diode is a semiconductor device that allows current to flow in only one direction. The symbol for it looks like this. It has an anode side, which is the positive side, and it has a negative side, which is the cathode side. The diode functions in one of two states. Both of these states are equally important. It can be operational in a forward bias state or a reversed bias state. Let's take a look at the individual states. First of all, the forward bias state. If you look at the forward bias state here, notice the diode is placed in the circuit so that the plus side, or the anode, traces back to the positive side of the voltage source, and the negative side, or the cathode side of the diode, traces back to the negative side of the voltage source. Whenever it's placed in the circuit like that, it's called forward biased, and it allows current to flow. And using Ohm's law through that resistor, we can determine what that current is. The current through a resistor is equal to the voltage difference across the resistor divided by the resistance. That's Ohm's law. So if you take a look here, we have E on this side of the resistor. On this side of the resistor, the first approximation would be, it could be ground. You could call it ground, but we're going to use a second approximation that allows for a voltage drop across this, because there is a voltage drop across the diode. Diodes are made out of germanium or silicon. Both are semiconductor materials. The most popular diode is the silicon, so we're going to use 0.7 volts as the forward voltage, or the voltage when it's in a forward bias state. So let's use Ohm's law again. Determine the voltage across the resistor with a second approximation. E minus the voltage on this side. Well, if this is ground reference here, you're at ground reference, and then you're up from minus to plus. You're up 0.7 volts. So VF is going to be 0.7 for this course for us, and you divide by the value of the resistance, and that's that current that flows in the circuit. And the current that flows in this series circuit is the same current that goes through the voltage source, that goes through the resistor, that goes through the diode, the forward bias diode, because it's a series circuit. Now let's take a look at the physics of this particular device in this diode in a forward biased mode. If you take a look here at my whiteboard, what happens is this diode gets placed in the circuit, and the anode is positive doped material. That's what they call it. And the semiconductor material at the negative side is n-doped material. So you have the semiconductor physics is you have positive material here and negative material here. Well, the positive material are whole charges, absence of electrons. And notice you have positive material, positive whole charges over here on the battery. And we know that like polarity, like charges repel each other. So what happens is the charge right here inside this device repel each other, so they get pushed toward that junction in this direction. And over here you have negative material, which is electrons, and you have negative down here, so they repel each other, and these negative charges push these into that junction, and this junction gets reduced. This depletion area in here gets reduced. It gets very, very thin, and that allows for current to flow. That's why you get, in a forward biased form, the diode conducts current. Now let's take a look at a problem here that uses this equation for forward biased on page 124. It says here, find the forward current in the following circuit if E is equal to 5 volts and the diode is silicon. Well, here's our circuit. Here's the equation. I plug everything in, I get 4.3 milliamps. What I want you to do is take this same circuit and find the value of RS in this case. That would limit the current to 20 milliamps. The reason we're going to do this is because this diode is going to be a light emitting diode for us coming up in some labs. It's going to be an LED. So when it's forward biased, it emits light. And the typical current through an LED is 20 milliamps. So I want you to calculate what resistance value this would be if you're going to drive an LED. It's a design problem. I want you to use this equation, and you're going to have a value of RS this time, and you're going to solve for, you're going to have a value of IF this time. You're going to solve for RS. I want you to work it out and see if you get 215 ohms. That's the answer. Make sure you know how to do both of these problems. Very important. What about in a reversed biased form? In a reversed biased circuit, the diode gets placed so that the negative cathode traces back to the plus side of the battery, and the positive anode traces back to the minus side. And dislike charges will attract one another. So these electrons get attracted to these hole charges over here that pulls it away from the junction. These hole charges here and these electrons over here, these hole charges get attracted to these electrons. And so what happens is, if you take a look down here, when it's in a reverse biased form, this depletion area widens. These electrons here get attracted to the hole charges over here, and these hole charges here get attracted to these electrons over here, because dissimilar charges attract one another. And this depletion area gets wider and no current can flow. That's the physics of it. The next semiconductor device we're going to look at is on page number 25. On page number 25, the transistor, a semiconductor device that has 3 leads. It also can be made of germanium and silicon, just like the diode can. Transistor comes in 2 forms, an NPN transistor, or on the next page you'll see a PNP transistor. That's the 2 forms that the transistor comes in. We're on page 125. Transistor has 2 junctions, not one. It has a junction that separates a collector and a base, and it has a junction that separates a base and the emitter. So this is the symbol for the transistor. It has a collector, has a base, and has an emitter. When you have an NPN transistor, and the way you can tell from the symbol is the arrow points toward the negative material. This arrow is pointing out, so it's pointing toward this negative material, so that makes it an NPN. You have positive material between 2 N materials in the physics of the transistor. It takes a positive voltage on the base with respect to the emitter to turn the transistor on. That's important. We're going to be using the NPN transistor this semester. So just remember, when you have an NPN, the base is positive, so it takes a positive voltage with respect to the emitter to turn this transistor on. When I say turn the transistor on, I mean, for our case, shorting the collector and emitter like a switch. When you put a positive voltage here with respect to the emitter, this point to this point is shorted. So it would allow current to flow through this output circuit here. You'll see that in a minute. The other form of the transistor is the PNP. And it's on page number 126. Looks like this. Notice that the arrow, this is the symbol, arrow points toward the N material. It's a PNP. The collector is P, the base is N, and the emitter is P. The thing to remember about this, since the base is negative material, it takes a negative voltage on the base with respect to the emitter to turn the transistor on. We're going to be using the previous example, the NPN transistor, though, but I wanted to mention this. The transistor has 3 states it operates in. It can be off, which we'll call cutoff, where the collector and the emitter is open. So when the transistor is in the off state, right here, when this transistor is in the off state, that's an open circuit between the collector and emitter. No current can flow. It's just a switch that's open here. When the transistor is in the active state, we're not going to concern ourselves with that in this digital class. We have a binary, either things are off or on. This is the next course. This is EE210. We'll talk about transistors in the active state. The third state is it can be full on, completely on, which we call saturated, where the collector to emitter is shorted. It's closed. In other words, when you're saturated, this is a short between the collector and the emitter right here. Current can flow through there like a closed switch. What you have to memorize for this course is state 1 and state 3. There's our two states. There's our binary states. Off, which we're going to call cutoff. That's the professional terminology for it. When the transistor is off, it's cut off, and the collector to emitter is open. When the transistor is full on, it's called saturated, and the collector to emitter is a short circuit. It's closed, like a closed switch. If you look at page 127, which will be the last page we're going to reference here in this lecture, let's look at the construction of logic circuits. This is going to be our next lecture, but I wanted to point this out while it's fresh in our mind. The construction of logic circuits. Here's an inverter. This is what the inverter looks like, and here's our truth table. The simple inverter circuit. What's inside that guy? It's, well, basically this. This guy right here. This is just the switch. Let's see how the inverter works using the transistor. And don't forget there's 6 of these inside a 7404 package. It's a hex inverter. So when the switch position is in switch number 1, the logic level for A is going to be 0 because it's ground. That's 0 volts. 0 volts on the base. Transistor's in cutoff. The collector to emitter is open. With this open, the output gets pulled up to 5 volts. That's a logic level 1. We're putting in a 0 and we get out a 1. What about when the switch is in position 2? When the switch is in position 2, it's a logic level 1 because point A gets pulled up to 5 volts. 5 volts on the base with respect to the emitter, it's ground, plus 5 and ground. You turn that transistor full on, which is saturated. The collector to emitter is shorted. When it's shorted, this point and this point's the same point. Output 0 volts, 0 logic level. You put a 1 in, you get a 0 out. That's how the inverter works. That's how you build that circuit with a bipolar transistor. Put in a 0, you get out a 1. You put in a 1, you get out a 0. That concludes the lecture.